we're here to chat with Lou Kauffman, and thank you, Lou, for agreeing to be with us. And I think I was just noticing that Lou describes himself on his webpage as, I am a topologist working in knot theory and its relationships with statistical mechanics, quantum theory, algebra, combinatorics, and foundations. And I know from a bunch of Lou's work that Lou is a serious foundationalist, interested in structures that seem simple at first, but end up building up to much more complicated things, which happens to be also a kind of topic that I've been deeply interested in for a long time. Although the kinds of things that Lou has studied with knots and other kinds of things are rather different from kinds of things that I've studied. So I guess I'm curious, Lou, and I probably should know this, but I don't. How did you get into knots in the first place?
Oh, I was taking a topology course at MIT when I was an undergraduate. And I think near the end of the course, I encountered a paper by Ralph Fox called A Quick Trip Through Knot Theory. And that's a remarkably good paper, which introduces you to a lot of ideas in that subject. And I got interested in knots that way. So I hadn't been tying knots when I was a teenager or anything. I got interested in actually tying knots sometime later.
Fair enough. But so what was the mathematical trajectory? So I mean, at that time, knot theory was kind of a branch of topology, or what was the mathematical character of knot theory at that time? Or was it kind of a thing out on its own that was kind of a separated area of mathematics?
Well, knot theory has long been near the beginnings of the development of topology. If you go back into the 1800s, you find that Lord Kelvin, Sir William Thomson, had the idea of that atoms would be vortices in the luminiferous ether, knotted vortices in the luminiferous ether, and he investigated the possibility of knotted vortices. Among other things, he couldn't prove that they were stable, and the theory had lots of difficulties, but it was the beginning of the theory of knots. And so the beginning of the theory of knots was physical.
Right. No, I mean, it's very interesting because obviously in our models of physics right now, we're interested in topological obstructions in these hypergraphs that we're, evolving hypergraphs and so on, which is bizarrely similar to the idea that Kelvin and I think Maxwell also had about atoms are knots in the luminiferous ether.
Well, surely you will run into defects in your graphs, things that are not quite smooth and are beginning to look like particles, possibly not yet knots or even knots. Do you get knots?
We don't think we get knots. We don't think it will be specifically knots. I mean, it's like in cellular automata, for example, one's very used to having these localized structures that are, that preserve their identity through time and move in space. And those are they're not topological defects, so to speak. There's some kind of computational defect that has a character that isn't quite, I don't think, has a topological interpretation.
Well, there's also a sense of recursion in a knot. I mean, if you look at a knot, it comes back on itself, right? It's some twist and it comes back on itself, and it feels like maybe that it's a three-dimensional, some kind of recursive form that is returning to itself. So when you think of moving defects in a cellular automaton, they're also recursive and moving, so they have some kind of knotty flavor to them, I think.
Maybe so. I mean, that would be very interesting if there was a way of connecting those kinds of things. But I'm curious. So I know that back in the I'm curious about the history here. I mean, back in the 1880s, 1890s, Maxwell had his friend Tate go off and classify knots and things, if I remember the history correctly.
Yes, that's right. And that was at the behest of Lord Kelvin, who really, really wanted those tables.
So they thought they might find 90 kinds of knots or something, and those will be the chemical elements.
Yeah, well, I guess they quickly realized that there was a huge infinity of knots, but I suppose they hoped that there would be some core set of knots that would correspond to atoms.
But so, okay, so that was the very beginning. So what happened next in knot theory?
Well, Tate and Little and Kirkman, they made the tables, and topology, and of course, concurrently, there was the development of differential geometry past Riemann and Gauss and so on, and Poincaré, and the beginnings of the development of algebraic topology. And so then, around 1900 or by 1905, there were people who are working, like Max Dehn in Germany, working on the topology of knots, using Poincaré's fundamental group to analyze the properties of the complement of the knot, topological properties, proving really very hard things, like proving that the trefoil knot is inequivalent to its mirror image topologically by looking at the way the fundamental group works.
Huh. So that was okay. So the relationship between knots and groups and so on was a very early thing. That was, I mean, because
yes.
Interesting. So what happened next?
Then by the 1920s, Alexander and Briggs started working on classifying knots, and Alexander invented his famous Alexander polynomial, and that's a polynomial which you calculate a polynomial from a knot, and the polynomial is essentially an invariant of the knot up to multiplying it by something. So this is much easier than looking at a group presentation and trying to try to divine whether this group presentation is trivial or not is very hard, right? But if you have a polynomial, it's either non-zero or it's zero, or it's not equal to that polynomial. So Alexander and Briggs did that, and they also found a set of combinatorial moves for understanding knots. So then knots became graphical. So you could think of them as graph theory with certain special tweaks and moves on those graphs.
But graph theory was not yet popular at that time, or is that not true? Had graph theory become popular by then?
I think at that time graph theory had not become unpopular. One had not reached the point where an influential topologist said graph theory is the slums of topology. That was a little later.
Who said that?
J.H.C. Whitehead is famous for having said graph theory is the slums of topology.
Interesting. Okay, but so back, I mean, when Tate was creating his tables of knots, he was also presumably trying to classify knots. I mean, he was saying
certainly.
But and when he drew pictures of knots, none of the pictures he drew were actually of equivalent knots, were they? Or did he manage to get that
right? Well, mostly he got it right. Yeah. So, but he didn't have invariants to calculate. All he had was his hands-on experience with, maybe he used rope models and maybe he pushed the graphs around on paper, but however he did it, you could generate all the graphs you need, but you would get many multiplicities, and then you have to start throwing them away. And oy vey, multiplicities means up to moving the things around. So, you might take a projection of this in one direction and you'll see a certain graph, and then you might move it around in space a bit. Whoops, I broke it. And you'd get a completely different graph projected in the plane. So it's a hard problem to classify them.
So I know you have a knot invariant named after you, and I guess there are about 3 or 4 knot invariants that are kind of famous at this point. Is that?
Well, now we're up along in the history to the time of von Jones. Maybe I should talk about the history a little bit more. There was the Alexander polynomial and many things related to it. And then along came John Conway around 1969. He made it public, but I guess maybe as much as 10 years earlier, he had found a beautiful way to understand the Alexander polynomial without using anything except graphs. Now, I really mean not using anything. You see, the way it was originally defined, you didn't use very much. You would take the knot diagram and you would write a certain matrix, and then you would calculate a determinant of that matrix, and there's the polynomial. But you went through algebraic mathematics, you went through determinants and things. Conway was a genius at doing things recursively, and he found a formula, a diagrammatic formula, which involves the knot and a smaller knot and a smaller diagram. And then you just keep on going recursively until you haven't got anything left, and you calculate the invariant. And it was a little bit better than the Alexander polynomial in some ways. So he discovered this, which we'll call the Conway polynomial.
But so I don't know enough about how this works, but I mean, so the idea is that you make a series of moves. You're sort of recursively making these moves to turn it into an unknot or something. I mean, you're going from the knot you have, and you're saying what sequence of moves do you need to make to get it to something you recognize, or to an unknot or something?
Yeah, I'll show you what it looks like.
Great.
So let me make a little drawing here. You can see that?
Yep.
So over here is a trefoil knot.
Mm-hmm.
And here's a crossing in the trefoil knot, right? Let me see there. This crossing is the one I'm looking at, yes.
Okay.
And over here is exactly the same diagram, but I switched the crossing.
Okay.
Now, this happens to be unknotted. So this is simpler.
Uh-huh.
And this one has been smoothed, we say, which means that you think of the 4 points near the crossing and you just connect them up so that there's no crossing at all. You see, like that.
Uh-huh.
So this is called a skein triple, Conway's notation, skein triple. And then there's a formula that Conway invented.
But so to know for a given knot, which of those moves?
So these are not moves yet. These are just graphical changes, right? And
Okay.
the formula, the beautiful formula, is that nabla, the polynomial of the one with this crossing, minus nabla of the polynomial of the one where we switch the crossing, is equal to nabla of the one where we smooth the crossing.
Wait a minute. By nabla you mean like
nabla k for some knot is equal to a polynomial as some polynomial in a variable z.
Okay. Okay.
Right. So you can think of this as a recursion formula that says this. Where am I? This one is equal to this one plus that one.
Uh-huh.
And the two on the other side are a little bit simpler. One is closer to being unknotted because you choose to switch a crossing to make it a little more unknotted. And the other one is simpler because it's got one less crossing in it.
I am still quite confused by this. You see, I'm really bad at 3D visualization. This is, I have to admit. So
okay. Well, keep asking. Keep asking.
Well, I mean, so those two first pictures, are you saying those are the same picture, but they have arrows in different places? Is that true, or is it?
No, look at the pictures underneath. All right, because these are schema. This is a schema,
No, I
but it'll be clear. This is a picture of a knot, right? Very simple knot.
Yes.
Look at this one for a moment carefully. It's not knotted because this little loop can slip right out.
Okay.
The convention being that when there's a break in the line, the rope is going underneath.
Okay. Okay.
Just like if I hold my hand up, you see a crossing that looks similar to what I drew, where the one that's nearer to you is over, and the one that's nearer to me is under.
All right, but so this, the thing you did there, you're making, I mean, okay, you're exchanging two, you know.
So the only thing I did was switch one crossing, just one, right there. Yeah.
Okay.
And then at that very same local site, I replaced it by a smoothing.
Okay, and that just ends up with two loops.
This could be reminiscent of something that happens in graph theory, where you delete or contract an edge, right?
Okay.
Only instead of deleting or contracting, I switch or remove. It is somehow related to the graph theory.
The thing that is slightly confusing to me is that, I mean, obviously you're showing a two-dimensional projection of this knot.
Oh, indeed, I am.
And you know, this operation, if I think about it in the, you know, in the knot embedded in 3 dimensions, this operation is you're taking presumably two things that were sort of crossed over like this, and you're flipping them. You know, one of them is just passing through the other to the other side. Is that correct? I mean, that's
right. It's not a topological move. It's a discontinuous move.
No, I realize that. Right. I mean, it's this thing is this finger is breaking in half and ending up on the other side of this finger.
Yeah.
Right.
Mm-hmm.
So, okay. So I mean, then this, but so what you're saying is, what I was trying to understand before is, given a knot, you have some very complicated knot. You are making these series of changes to that knot. Maybe you don't call them moves, but these changes to the knot to turn it into something that you recognize. Is that
what I'm doing is describing to you Conway's remarkable algorithm to calculate his polynomial. Okay. The moves that we do on knots are much more like what you would do fluidly in space. So, for example, if I have a bit of rope and another bit of rope, is that visible? And it's one of them is going underneath the other. I'm trying to get that in camera.
No, you see it, yeah.
And I pulled them a little bit. They come apart, right? So that looks like that's a move you could do on the graphs.
Yes.
Or if you saw in the graph, you saw a twist like this. You could untwist it like that. And there's another one which is a little harder to do, where you have one is two things are crossed over. Oh, let me try it. Two things are crossed over like that. And there's another arc like this. And it could slide up and down between them like that. Yeah. So it turns out those three moves are enough on the graphs to generate all the changes you would like. So if the knot is unknotted, you could undo it by those moves.
Right. But so
now the Conway thing is kind of perpendicular to that. It's a method of calculating in the diagrams that will give you a polynomial that doesn't change under those moves.
Okay, but wait a minute. But the point of these knot invariants is that different presentations of the knot have the same value of the polynomial.
Exactly. Right.
But these moves, if I'm understanding correctly, these are actually changing the knot. I mean, the
moves in the skein relation change the knot. You're looking in a family of knots. Instead of looking at the original single knot, you're looking at all these nearby knots, one switch away, two switches away, three smoothings away. Right.
Okay.
And they all turn out to have invariants that are related to one another by a simple formula.
Okay, I think I get that. Yeah. Okay, so then this was the next. You were describing kind of the trajectory.
Right. Historically, that's really an important place, because he discovered that you could do this for the Alexander polynomial. You could create it that way, rewrite it that way. And then, for whatever reason, he didn't ask the question and nor did anyone else ask the question, why are these coefficients being used? What if you said twice this rather than just multiplied it by 1? What would happen? What's the general case? A times this, B times that, C times that. Nobody asked this question until probably 1983, when von Jones invented, by quite a different method related to physics, another polynomial with different properties that satisfied a relation of the same kind.
With particular A, B, and C, or with general?
Yeah, with particular A, B, and C, a different A, B, and C. And this one could do things like tell the difference between the truffle and its mirror image, which the original one couldn't do. And so that led to a lot of excitement, and people started hammering away at it, and we discovered that there were other polynomials in there beyond the Jones polynomial. And well, one of those happens to be named after me, and also a particular way of getting at the Jones polynomial is something that I found. So that was very exciting and purely combinatorial at that point.
So if you take all the knots that are in like Tate's book or something, are they distinguished by, I mean, given these famous knot polynomials, can you distinguish the knots that are in there? Can you distinguish all the knots that are in there with those polynomials? Or would you need more?
If you allow me to do some trickery, you probably can, but the trickery is a little technical for computational purposes. If you take one of these polynomials and instead of looking at the knot, you calculate the polynomial for the knot after you've replaced the lines in the knot by some number of parallel lines, you can make the knot more complicated in a regular way. Just make it into a cable, and then calculate polynomials. Then you can do a huge amount of discrimination. How much exactly you can do, I'm not quite sure. There still may be some duplications if you're only using these knot polynomials. But there are examples of knots that have the same polynomial.
But so
lots of examples.
What's the decidability? I mean, in terms of at a computational level, so to speak, theoretically, is it a decidable problem to figure out whether two knots with certain presentations are equivalent, or is that
yeah,
or is it?
Yeah, it is a decidable problem, but not by the knot, and not at the present time by knot polynomial techniques. It's a decidable problem by three-dimensional manifold techniques.
Where you're effectively, I mean, it's like a bit like graph isomorphism, where you have to just make lots of, where you can make, there's a bounded set of changes that you could imagine making to get from one knot to another. Is that kind of the concept, or how does that, how should one think about
the
that?
concept is understanding the structure of the three-dimensional complement of the knot. You triangulate that space up and then examine its properties.
So did that fact require things like the whole Thurston three-manifold equivalence business, or was that independent of that kind of?
The Thurston three-manifold business can be used to get very strong invariance of knots, but this particular kind of three-manifold work for discriminating knots, it doesn't depend on the Thurston geometry.
So it's something where, I mean, if you have, for example, a simplicial decomposition of this three-manifold thing, is it then a finite? I mean, is there sort of a finite mathematical way to just determine whether these two simplicial decompositions of something of two three-manifolds are equivalent? I mean, is that sort of what you have to do, or is?
Yes, that's right. It can be turned into a basically finite problem about linear algebra in the end.
But so as you make bigger and bigger knots, does it get computationally? I mean,
well, this gets computationally out of hand right from the beginning. This way of doing it.
But is it known? I mean, I sort of vaguely remember some results about computational complexity of determining knot equivalence and so on. Is there any kind of level of lower bound or NP completeness or something like this that's known for that equivalence problem?
Well, calculating knot polynomials is NP hard, and determining whether a knot is unknotted is another NP problem.
Interesting. Okay, so I see. So
but I should mention that the diagrams eventually did come back I mean, at first, the work of Hopfion and Hopfion is the work that we were just referring to that can tell whether two knots are different. And it used the complementary three manifold. But you might wonder, well, why can't I just look at the knot diagram and tell whether it's knotted or not? Suppose it's just knottedness, you'd like to know.
Mm-hmm.
Well, the problem with these kind of diagrams, the kind I was just telling you about, is that you can draw an unknot, but in order to unknot it, you have to make the diagram more complicated before it simplifies. And we don't have a really good handle on how much more complicated we need to make it. The upper bounds are not great that are known.
But so if I were to make...
yeah. A Russian mathematician working on this problem realized, his name is Dyenikov, Ivan Dyenikov. He realized that a different diagramming system, a different graphical system, allows him to search a bounded space to see whether or not is unknotted. And the kind of diagram it is it's amusing that some other elementary kind of diagram would do it. I'm drawing just without crossing overs or unders. It's just a rectilinear diagram, vertical and horizontal.
Yep.
Right. And if you use those kind of diagrams on a different set of moves, then you end up searching a bounded space to find out whether or not is knotted or not. But we don't know yet what happens for discriminating one knot from another.
But so if you look, presumably you can enumerate all possible such rectilinear, paths and so on in the plane.
Sure. Like if I want to eliminate or enumerate all the ones that have three verticals and three horizontals, I can enumerate all of them.
Right. So, I mean, a question would be, if you enumerate all of them, so for example, there's statistical questions you can ask. What fraction are unknotted? What is the peak? It's like an algebraic simplification problem or something where the thing can get more complicated before it gets simpler again. What does that distribution of sort of intermediate complexities look like? Does it get, for example, exponentially bigger at the intermediate stage, or does it stay? Is it as you increase, for example, the number of horizontals and verticals, does it stay kind of polynomially bounded, or does it appear to in the sort of the peak of that of the sort of intermediate expression, so to speak?
Well, I don't know what those statistics look like. There may be some literature on it, and we should look at it.
Yeah, somebody should look it up. I mean, we could probably do an experiment.
We can also put it in Mathematica and get
right.
some things off of it.
Right, but it's interesting. But I mean, so and presumably, I mean, it's a kind of a nice theorem proving like problem, because presumably what you're trying to do is you're trying to ask, is there a sequence of moves that will lead you to the obvious unknot, so to speak? And in general, you'll end up with some, in our world of our kind of physics models and things, you'll end up with some multi-way system, some graph of possibilities of what would happen with all these different moves. And then the question of whether it is the unknot is, does there exist a path which will get you to the unknot configuration? And I mean, that's a quintessential kind of theorem proving type problem of finding, does there exist a path that gets there? I mean, I'm curious whether people have people enmeshed sort of theorem proving with knot investigation?
Well, the best programs that I know that have been written so far are just to randomly search that space, and every time it got reduced, use that reduction, and it'll quickly unknot some small knots. But I have wondered whether you could take that game of searching and reducing and put it into a neural network machine learning environment and get the machine to become very good at doing it, and then learn something about efficient pathways that way.
I guess
that project hasn't quite been started yet by people I know.
But I mean, the other question is whether you can use theorem proving techniques where you're using things like these completion, adding completions and things like that to be able to maybe somebody here maybe Xerxes knows something, can see whether this is, or I don't know if Jonathan is here, but
well, let's see. I ask you the question then. Have you done that in other graphical domains? You're talking about the following scenario. You have graphs with certain combinatorial moves on them and a bounded search space, but you want to apply theorem proving type techniques to reduction. Have you tried it in some other problems?
Yes. I mean, I think maybe Xerxes can say something about this. I mean, in particular with this, in the ZX calculus business, for looking at quantum circuits and so on. That's a story of I think it can be thought of as a story of simplifying graphs by moves. Xerxes, do you want to comment on that?
Right. So in the ZX calculus is just a set of diagrammatic reasoning in which we have a finite set of equational rules. And over there, the goal is to simplify an initial diagram to something simple. It's not that there is an analytic way to do it. There are optimization methods in which people try to use some kind of empirical trick, as in looking at those pathways where there are maximum causal edges so that you can start reducing. So it's really, it's more an empirical optimization method that is being used there. That's about how far we've gotten. Maybe the point I'm trying to make is that even over there, one cannot be sure that one has found a global minima.
Right. I mean, none of these methods, none of these kind of combinatorial optimization methods, they're all going to be heuristics. People have tried using machine learning to figure out, what's the best path to try taking in this kind of search space. And I think those have been modestly successful. I mean, recent experiments that Xerxes and Jonathan and Mano have done on simplifying quantum circuits using ZX calculus use, I think, a slightly more principled approach that is based on our physics project and this thing about flux of causal edges and so on. But it would be a good thing to try for knots. I mean, this is
but for knots over here, if one has to do it for the case of knots, then the question one is asking is the following: from the multi-way perspective, does the multi-way of this knot terminate under the under the Rademacher moves? Right. That's the question one is asking. If it terminates, it means that one has reached probably a point where no further moves can be applied.
Yes.
Yeah, you see how the problem of unknotting is much simpler to think about in these contexts than the problem of is this one equal to that one? Because with the unknotting, you can actually try to reduce something and get it to become some symbol. And if you have two things, you don't know what you have to do to get from one to the other. And so it's much harder.
Right. Although in the context of these multi-way systems, what you're asking there is there a path from one point to another point in a multi-way system? And, in the case of what you're saying about unknotting might be some kind of energy function that is like number of crossings or some other thing. And you're saying sometimes that has to go up before it can come down, but there's some notion of progress, so to speak.
That's right, and in fact, energy function is another way to go. You can coat the knot with fake electric charge and let it repel itself, and that often unknots, but sometimes also gets in trouble with needing to go up energy in order to get down farther.
Is that what happens? I mean, DNA that gets knotted, does it have? What happens? Okay, I haven't really followed this in recent times, but there was a time when people were very, very keen on knotting in DNA. Did that pan out? I mean, is our DNA?
Oh well, it's part of nature, and the fact that the knotting that happens in DNA can be controlled is controlled by enzymes in the cell called topoisomerase by the biologists, and those enzymes do the following sort of thing: something is linked, and the enzyme comes along and breaks one of them and allows it to slip through and then puts it back together. And a flock of enzymes working on the newly duplicating DNA manages to allow the two new DNA double helices to come apart in order for the cell to divide. So the knotting is really being worked on in the cell by real mechanisms.
but those are all local. I mean, I can't believe that anything is figuring out globally whether the thing, it's not solving.
I don't think there's a homunculus down there that's working out Mount polynomials.
No, that's the, but so really it's a local thing where it's seeing that there's, you know, that there's a particular local, how does it know? I mean, in the enzyme, when it binds to that structure, does it basically have a template, which must be the knot complement actually? Is the shape of the enzyme kind of a template that looks like the knot complement of the of these of a pair of knotted things, and is that how it? I would guess that must be how it works.
Well, I don't think it looks like the whole knot complement. It's just designed to be able to fit around a couple of strands that it needs to switch. Right.
Right, but I mean, it's kind of the trick that it's like the immune system trick. The immune system doesn't recognize the whole sequence of the virus. It just recognizes a small, whatever it is, 12 base pairs or whatever the number is for it's just recognizing this small kind of signature of this is this is an antigen, so to speak. And so I would sort of guess that there must be a local signature of knottedness that enzyme is recognizing. I mean,
yeah, it must be. I mean, I don't know exactly what it looks like, but a local signature of nearness of strands that could be moved across one another.
I see. So it's like it notices that the thing has kind of connected like that, where two strands are trying to move apart and can't get apart. And so it's I mean, that's the kind of thing that it could know locally.
Yeah, I'd be willing to go with your guess that that it might be able to recognize a class. But if I have something that goes this way and the other one goes this way, then
right.
Maybe that's recognizable enough to know that you would like to clip that and unhook it.
Yeah, that's cool. That it might be actually making some knot complement like thing. That's very bizarre. So actually, we had some questions here on the chat. So what's being said here? There's a question from
I've
Roman.
got your book, actually. I just realized I have the...
Oh, yeah, I know that book. Yeah.
Right. That's good. So you've got how old is that book actually? When did you write that?
87, that book.
Okay. But so Roman here was asking about Reidemeister moves and whether what the relationship, what you're describing is to those moves.
Yeah. Reidemeister moves, let me draw a picture again. Reidemeister moves are the moves that I was waving my hands at in the air a moment ago. So you may recognize what I was doing with my hands when I draw the moves for you, but these are the local changes that are called the Reidemeister moves.
Right.
And by the way, they go all the way back to Maxwell.
Oh, okay.
Maxwell played a lot with knots and drew the pictures of them, and one can see in his notebooks that he was doing these sorts of moves. I don't know that he proved a theorem about them, but by the time the 1920s came along, Alexander and Briggs proved that those moves were sufficient. And they're called Reidemeister moves by the well-known tradition in mathematics that you always call a theorem that was proved by A by the name B. Yes. Particularly if B writes a book about it.
I see. Okay. That's some... but yeah, I think Maxwell wasn't so much in the theorem. I mean, Maxwell was actually a pretty clear expositor, but I don't think he was a theorem, writer. He was more of a physicist deriver of things. So he wouldn't have qualified by a mathematical definition of those things, perhaps. But so in your own, okay, so.
Before we move on, could I just quickly ask the name of that Russian mathematician who invented the rectilinear graphical diagrammatic notation?
Yeah, his name is, I'm writing it in the chat line.
Thanks.
Oops. And he didn't actually invent the notation, but he applied it to this problem. I'm going to write a key word in case you look in the archive. There's a paper with monotone in the title.
Okay, thanks.
And how old roughly is that work?
2005 or 6.
Okay. But okay, so now in terms of your own trajectory, well, let's see, we were talking about knots and the identification of knots and so on. I mean, has that been the main kind of thrust of knot theory? Is this question of knot equivalence and so on? Is that kind of the main sort of mathematical holy grail of that field, or are there quite different directions that the field has gone in?
Well, the general problem for knot theory from the very beginning has always been the question of what can you tell about the way one space is placed inside another space. So the knot theory we're talking about is how can you classify how a circle can be embedded in three-dimensional space.
Mm-hmm.
So indeed, the holy grail of three-dimensional, not one-dimensional knots in three space is to be able to know whether two knots are equivalent or different. But then there arise all sorts of very interesting problems within that, like understanding when a knot is an alternating weave, understanding when a knot bounds a surface of a certain kind, or most particularly, does this knot bound a surface in four-dimensional space is a great problem, which has been investigated a lot. So you have this knot, which is highly non-trivial in three space, but nevertheless it bounds a disk in four space. There are such things.
So I see. You're saying in four space, when you project it into three space, so you have this thing in four space.
The knot is sitting embedded in three space,
mm-hmm.
but three space is the boundary of four space.
Yes, I see. So I see. So there are non-trivial knots. I mean, like something like a trefoil knot. Is a trefoil knot a boundary of some very smooth, simple object in?
Right. So a trefoil knot will bound a punctured torus in four space.
I see. And that's
the best you can do for a trefoil knot. It doesn't bound a disk. Now, I should try to make this idea a little more concrete for you. Suppose you have a knot and you allow, looking for some, well, I'll just do it with my fingers, and you allow two arcs to come near one another and reconnect like that.
Uh-huh.
Vortices reconnect like that, for example.
Uh-huh.
One-dimensional vortex can reconnect like that.
Uh-huh.
If you think of that, if you think of the time track of that action, what happened was that you went through a saddle point. You traced out a surface in four space in the world line of the knot, and you went through a saddle point. So you see the history of the knot changing like that becomes a surface in four space.
Right. Yeah, I mean, we would love to understand for in our models, right, where we have these updates of graphs, we have these moves that happen on graphs. We don't have a good sense of, we in principle, you could imagine embedding what we're doing in continuous time and having this sort of this surface that is a membrane that joins one graph, one form of the graph to another form of the graph.
Mm-hmm.
And that would be an example of something which would be, like what you're describing, and we have no idea what the algebraic structure of that surface might be. I mean, so what you're saying is, for example, in that, is there some theory then of when you have, if you're using this knot to bound, as the boundary of this thing in four-dimensional space, there's presumably an algebraic description of the surface there can be an algebraic description of the surface that you get in four dimensions, that of which the knot is some I don't know, algebraic variety or some other algebraic geometry type of thing.
Sometimes you can describe it as an algebraic variety. That's right, and that's another sub area of the knot theory: knots that can be described by algebraic varieties, or knots that are described in terms of singularities of algebraic varieties, where you can have a singularity of an algebraic variety in four space, and you look at what happens nearby, and the intersection with a small three-dimensional sphere near the singularity ends up being a knot.
Okay, that's interesting. How does that relate? I'm just curious in terms of the development of these things. I mean, the whole catastrophe theory story and so on about did that I don't remember any knottiness in the catastrophe theory stories.
That's a failing on our part, I think, because we all knew that the cusp catastrophe was giving us a trefoil knot if you just made X and Y into complex variables. Now, I never thought about it until you asked this question just now. I mean, I'm always aware of that relationship, but what does that do to the dynamics of the cusp catastrophe if we think of the catastrophe variety over the complex numbers instead of over the real numbers?
So you're saying, I mean, basically,
I'm saying y squared minus x cubed equals a constant. That's the cusp catastrophe, right? And if you look at that over complex variables the way I was talking about, it gives rise to a trefoil knot.
Very interesting. Okay, and is that I mean, so in fact, is the classification of catastrophes equivalent to a knot classification, or is that I mean, are those things, you know, because there was the whole story of these different mappings in catastrophe theory of different, you know, different
right,
orders of algebraic surfaces and things into I mean, is that somehow equivalent?
No, I don't think it's equivalent to a knot classification, but it's a very interesting classification. Of course, you're classifying these up to certain deformations of the equations. The story is very well told and probably needs to be thought about all over again. The public discussion of it, I think, stopped too soon. Right.
Yeah, it got too applied too quickly, probably. But let's see. There's a question from James here about can any computational lessons be learnt from the Kirby calculus? Maybe you should explain Kirby calculus and the whole Rob Kirby. Well, I don't know about it.
Yeah, let me try to say what Kirby calculus is about. If you have a three-dimensional manifold, like the three-dimensional manifolds are the analogs of surfaces, but they're three-dimensional, locally Euclidean, and we're thinking of compact, so they don't have boundary, and they're just nice round things like the three-dimensional sphere. But there are other examples, like you could take a two-dimensional sphere Cartesian product with a circle. So you take a two-dimensional sphere and run it around in a circular form, and that's a nice three-manifold. Not one you can put directly into ordinary three-space. Many of them don't fit into ordinary three-space. Or you could have the following, which is almost visualizable. Take a cube and identify the top face with the bottom, the left face with the right, and the front face with the back. And you can describe that as the Cartesian product of three circles, three periodicities, a threefold periodic space. And some people have speculated that the universe is obtained by taking a dodecahedron and identifying opposite pentagonal faces with each other, the geometric universe. Well, it's a nice geometric universe. Whether it's ours is another question. But anyway, one would like to classify three manifolds. It turns out that every three manifold can be obtained by taking a certain link in three-dimensional space and cutting out a neighborhood of the link, one tube for each component, and then putting back in the same kind of solid tori, but in a different way by a twist, and then you can get any three manifold.
Okay.
So Kirby calculus is a way of dealing with three manifolds that are represented by links. So instead of having a three manifold, I have a link picture. Only I have more moves. I can do Reidemeister moves, but I can also do things that are really only understandable if you look at the three manifold from a four-dimensional standpoint. The reason I say that is that this cutting out and putting back looks like this. Here is three-dimensional space, and here is a curve in three-dimensional space, and here is a disk whose boundary is that curve, and you attach it to the three-dimensional space, and then thicken it up and take the new boundary. It's the analog of, I have a bit of square here, and I have a couple of points in the boundary of the square, and I attach a one-dimensional curve to the boundary of the square, and then I thicken that up and take the boundary of the resulting thing, and I've changed the upper boundary of my rectangle to a circle and another curve that goes up around. The same thing happens one dimension up, and you get a new three manifold, 2 dimensions up, and you get a three manifold, a new one. Well, then these handles that you've added, they can, as you see, you're now out in 4 space looking at these handles, or 5 space looking at these handles, and they're moving around one another, and a handle might go up over another handle and come back down on the other side. And then what happens to the links down there? The links change by some moves, and those moves are called Kirby calculus. So Kirby articulates a set of moves on links that are exactly the equivalent to doing homeomorphisms of the 3 manifolds.
Okay.
So 2 3 manifolds are homeomorphic if and only if the corresponding links are Kirby equivalent.
So that's the thing.
I'm reluctant to draw the pictures of the Kirby calculus move, but then he asks, well, what about computation? Well, you're faced with a very hard computational problem. You might have a link, you might have a picture which you're sure is actually homeomorphic to having no picture at all. That would be just the 3-sphere. So these moves ought to work in such a way that they would all disappear. Some links can disappear. A circle with a little twist on it can disappear. So it's possible for the picture to just disappear. You have this link in front of you and you want to know, does it disappear? Poincare conjectured that it would disappear. He didn't know Kirby calculus, but if you take Poincare plus Kirby, then you get the conjecture that it will disappear if if a certain group that you compute is a trivial group. But now you have a terrible problem in front of you. You have this group which is a trivial group. Maybe you verified that it's a trivial group, but how are you going to find the moves in this calculus that will undo the thing? But and nobody could do it. Okay. Still nobody can do it. Someone else comes in, Perelman came in and proved the Poincare conjecture by using differential geometry and flows and Ricci flow and a lot of beautiful geometry, but it's coming in from a different angle, and the problems about the Kirby calculus remain.
So what you're saying is, I mean, thinking about the Poincare conjecture, you're saying that the original attempt to kind of discretify the problem of equivalence of 3 manifolds didn't end up being able to answer the question, and the actual approach with Ricci flows and things like that was more of a continuous deformation approach to things.
Yeah, that's right. That's right. I mean, you have a lot of that, I think, in the knot theory, that you have certain discretizations that are very cogent, but if you stick to them alone, you run into problems that you can't easily solve in that domain.
So do you have an intuition? I mean, like the 4-dimensional equivalence of 4 manifolds, which we know is undecidable in general, is there an intuition? I mean, you know, the way of approaching that one, I would suppose, typically might think about is a discrete math way of looking at the equivalence of, you know, of imagining a computational process for looking at equivalence of 4 manifolds. And I'm curious whether there's an obvious intuition about why, I mean, you know, why does, for example, Perelman's type of approach work for 3 manifolds, but not for 4 manifolds?
Well, the undecidability for 4 manifolds is related to the fact that the decision problem for arbitrary finitely presented groups is undecidable.
Right.
So
but that depends on the... I mean, it depends on what group what group does the manifold throw up, so to speak?
Well, the problem is the manifold can throw up any finitely presented group you like.
But that's not true in 3 dimensions. Is that true?
Yeah, there's more restrictions there.
And there's enough restrictions in 3 dimensions that it can be decidable. But in 4 dimensions, is it completely arbitrary, or is it just it's sufficiently broad that it ends up being undecidable?
You can get an arbitrary finitely presented group for the fundamental group of a 4 manifold.
Oh, okay. That's so let's see, we have all kinds of questions here, and then I wanted to ask some more things, but let's see.
Is there, wait, can I jump in for that one really? Is there a nice space of 4 manifolds in which it is decidable that is non-trivial? Like, what's the smallest sort of space where it's interesting but still decidable?
Good question. I don't know.
Let's see. There's a question here about Witten's knot invariance, and there's a question about sort of what the physics behind those knot invariance is, and I mean, they came from the topological field theory kinds of things, as I recall.
Yes. Well, the original paper of Witten, the one entitled Quantum Field Theory in the Jones Polynomial, Witten was inspired by Atiyah's asking the question, shouldn't there be some quantum field theoretic interpretation of the Jones polynomial? And he found it. He found a gauge theoretic interpretation of the Jones polynomial, actually. So the idea is very simple geometric physics idea. In a gauge theory, you have a generalization of differential geometry. In differential geometry, if you parallel translate a vector along the manifold and come back to where you started, it can change its direction a little bit, or a lot, depending on the trajectory that you moved around. So you calculate this holonomy to get at the curvature. And if you go around an infinitesimal loop, then you get an infinitesimal change that you measure, and you get the curvature of the gauge field, or the curvature of the differential geometry. So it's all of a piece. It's just differential geometry. So Witten's idea was you take the knot as a curve in 3-dimensional space, and you measure the holonomy and a gauge field on the 3-dimensional space. Now, I should say that what I mean by a gauge field is actually a something whose derivatives give rise to the field that you're really interested in. So, for example, if it's electromagnetism, then the gauge field is actually gauge potentials. And, you know, when you differentiate them, you get the electromagnetic field. The differentiation is actually the same as the curvature calculation. So that's the way it works. And holonomy means to measure that infinitesimal change of a vector as you go around a loop. And the holonomy I'm interested in is the trace of that linear transformation, just to be technical. So then you take the holonomy along the knotted loop. And this is not an invariant of the knot, but it varies. When you make a tiny change in the knot, it varies in relation to the curvature, of course, because it's an infinitesimal loop. So then he understood that if he integrated that holonomy over all the different gauge fields against an appropriate weighting factor, he could wipe out the curvature dependence and get an invariant. And he did it, and it works. It works, except that the integration is formal.
So let's see, that's an intuition that I'd like to understand that intuition better. I mean, so what you're saying is, this is, I mean, a very naive kind of thing. I mean, that, you know, when you're trying to find sort of topological type information from, it's pretty common to say, you take some, you know, for example, it's easy to find the genus of things by just using what's it called, oh gosh, when you integrate a vector field or something.
Oh, the Gauss-Bonnet theorem,
Yes,
or the
yes, yeah, those kinds of things, right?
You integrate you integrate the local curvatures on the surface, and you can pick up the curvature.
You pick up
Right.
things like the genus of the surface.
I mean the genus.
Right,
yeah.
right. So I mean that's an example of where you have local differential information and you integrate it over the whole thing, and you get topological data out. So
Right.
is the way to think about this Witten not invariant? Is that the same general kind of idea of you're sort of integrating some local differential information, and you find and the result is some sort of topological fact about the whole space?
Yeah, but it's a big integral, just like in quantum mechanics when Feynman tells us that if you want to find the probability amplitude for getting from here to there, then you just look at all the different possible paths that can go from here to there, and you take the integral over them in the right way, and it'll give you the amplitude. But it's huge. It's a huge integral. And this is, and in quantum field theory, in principle, you could integrate over all the different field configurations.
Right, right. So this is saying, I mean, this is something where you're integrating. You have all possible forms of the vector of the a mu or whatever, and you're looking at all those possible forms, and you're asking for all those possible forms weighted in some way, what is that integral? And that's the thing that you say determines properties of this knot. Is that right?
That's right. And then the gauge field is given in terms of a certain representation of a Lie algebra. And so then it turns out that the SQ2 Lie algebra gives rise to the Jones polynomial, and then other Lie algebras give rise to other knot polynomials. And so there's this incredible connection between Lie algebras and knot invariants that is first arising, well, not quite, almost first arising out of Witten, really first arising out of Fadeev and Rashitikin and Takhtajan and Drinfeld and those people who were doing it at a statistical mechanics level.
But so is it the case that sort of any Lie algebra leads to a different knot invariant, or is it just particular?
Yeah, almost like that. Yeah, I mean, you're going to need some conditions in order to make it work, but
is there some amazing thing with like the E8, Lie algebra or something leading to some particularly exotic knot invariant, or is it like SU2 is about as good as it gets?
No, there are exceptional Lie algebra knot invariants as well. Yeah.
But so in what was the statistical mechanics that led to, what was the what was the kind of how did it come out of statistical mechanics?
Well, this goes back to what's called the Gang-Baxter equation.
Oh yes, I remember.
And you may have heard that term or even played with it. Well, the Gang-Baxter equation is a matrix equation, and
so it's like in electric circuit theory. It's like the star delta transformation of electric circuit theory.
Exactly. That's a special case, right? And written in the knot diagram form, it looks like this: that a certain diagrammatic tensor that corresponds to this guy here would be the same as the diagrammatic tensor that corresponds to this guy over here, where I moved the line. Right, third Rademaster move. But star triangle is a graphical dual of this.
And so, but I mean, in the interpretation I know, like in electric circuit theory, it's a thing where you're working out the resistance of some network of resistors, and it's a way of saying, it's a way of simplifying the problem of working out that resistance.
Yeah, exactly. And for Baxter, he's looking at lattices on which he writes a statistical mechanics function, maybe a lattice with 4 valent nodes, right? And along every line there's a spin and there's a weight for each node, and you're writing a partition function, a statistical mechanics function for that. And he wants to find the eigenvalues for the tensor expressions that come out of that network.
Right.
And it occurs to him that if he could have the matrix that corresponds to one little crossover line commute with these big bunches of stuff, then he could find the eigenvalues because of commuting matrices. So it enabled him to solve his models in some cases, to have this commute with all of that. And this is the simplest, where is it? This is the simplest case of the thing in the circle commuting with the gadget that's over here.
I see.
I'm saying that every time I draw a picture, there's a matrix associated with the picture, no matter how complicated. And people call that tensor nets these days. So I just say the tensor associated with the network.
Right. Yeah, we've been looking at some of these kinds of things, actually. Yeah, I wonder, I don't know, Carlos may be here or he may be asleep because he's in Europe. And he may have to watch this on replay. So then he'll be asking, why didn't you ask about this? Okay.
What I was saying about Gang-Baxter. So Baxter was studying those and finding some solutions to them. And Yang realized that he could think of it in terms of particle interactions. And then it's really the same picture, just turned on its side. You could imagine time going up on my page and space going this way, and some particles interacting like that, in a one-dimensional space and one dimension of time, a toy model. And he wanted to be able to understand some things about that toy model. And he thought, well, it would be good if the scattering amplitude that I compute here doesn't depend on anything except the permutation that the lines make. And that would mean that if you slid the lines around but kept the endpoints, initial to endpoints, the same, you get the same result. And that's the Gang-Baxter equation a la Yang.
What was Yang's, when was that? And what kind of particle interactions was he looking at? Do you know?
I don't, I could look up when, I could look up the when, but it's in the 60s. But I'm not sure.
So that was
whether he, I'm not sure why he was looking at those models.
I would guess that was the time of Reggie calculus, and I mean, I don't know. It might have been scalar field theory, or it might have been some Reggie calculus thing. Yeah. Okay. Interesting.
Well, I have a collection of Yang's papers somewhere in my collection here. I'll you sparked me to look it up. I'll write you an email.
Yeah. I'd like to know.
But then the story.
Yeah.
You see, this got developed, and it's getting developed through Yang and through Baxter, and it going along. And these Russians start looking at it. Fadeev, Reshetikin, Takhtajan, and they begin to realize that to understand what these solutions are has something to do with Lie algebras. And I don't want to explain why, but if you start to think about it, you really begin to understand that it has a lot to do with Lie algebras. And then Grenfell comes along and shows, in fact, that there's a way to combine Hopf algebras, which are generalizations of Lie algebras. You can combine a Hopf algebra and its dual, and they make solutions to the Gang-Baxter equation. So there's all this beautiful theory that is getting created around that part of the statistical mechanics.
You mentioned Atiyah had the idea for the Ed Witten invariant. Do you know what drove him to have that idea? It seems like such a crazy idea, but maybe it's not so crazy. Like, why would Atiyah suggest to Witten to explore this?
I'm going to guess.
Go ahead, you guess.
Well, I'm going to guess. I mean, Atiyah had been deeply involved in applying kind of applications to gauge theory and instantons and these kinds of
that's right.
Sort of topological classifications of gauge field configurations and things like this. my guess is, I mean, although that, that stuff was happening in the 1970s, I think that probably, I don't know when this sort of was, I'm going to guess it's the late 80s was the time when.
Mid 80s, yeah.
Mid 80s, okay.
Sure.
So there wasn't.
Yeah, so Atiyah was always looking to see whether some topology might be related to some physics at that time.
Yeah, I remember because I interacted with Atiyah when I was in Oxford back in the 1970s, 1977 type time frame, and they were always very, very hopeful that this would kind of solve QCD and allow one to sort of break open everything in physics. But actually, very elementary kind of physics estimates showed that that was completely implausible, that these instant-on configurations in QCD couldn't be that important in what you would actually observe phenomenologically in QCD. But that didn't matter to the mathematicians. And it led to interesting mathematical physics that didn't have much to do with QCD, I think, in the end. But let's see, we had a bunch of other questions here, and Raphael is asking, are there other knot invariants that have physical derivations, like the Witten use of quantum field theory? I mean, there aren't a huge number of knot invariants, are there?
Well, we've mentioned this class of knot invariants that can be represented through gauge fields. Some people have tried to generalize that to knot invariants of two-dimensional spheres or surfaces embedded in force space by a similar method, and that has not gone too far. On the other hand, there are variations of statistical mechanics sums that give rise to knot invariants, and that would fit into as an answer to your question in a way. But then another thing happened, which is very startling indeed. Well, two more things. One thing was, if you take the functional integral, you can take its perturbative expansion. And then you have the coefficients of the perturbative expansion, which are expressed in terms of Feynman diagrams in the usual field theory. And that means certain sums of actual integrals, those coefficients. Well, those will, of course, also be knot invariants if you articulate it correctly and you started with a knot invariant. And they're called Vasiliev invariants by the topologists, because there was this topologist, Russian topologist Vasiliev, there is this Russian topologist Vasiliev, who had the idea to study knot invariants in a somewhat more general way. And it turned out that the coefficients of the perturbative expansion of Witten's integral fit his bill exactly.
Wow, okay. But now the actual Feynman diagrams, I mean, clearly you could imagine actual Feynman diagrams which are somehow knotted. I mean, is that relevant?
Oh, that might be. But I don't know anything about knotted Feynman diagrams, really. What this theory does is it has knots. Well, I do and I don't. I mean, you could have a knot, and then attached to it are various filaments that are part of the Feynman diagram in the perturbative expansion. And then those filaments plus the knot correspond to terms in that perturbative expansion. So those are knotted Feynman diagrams, but I don't know if they fit the bill you were thinking of.
No, I mean, that sounds like it, but I mean, I guess one could imagine in a Feynman diagram expansion, one is going to generate some number of, I mean, for example, in the large N expansion, for example, if you take, SUN for large N, you get this feature that you only the planar diagrams survive, so to speak. And so one might imagine that there was some similar kind of, maybe this is a well-known thing, but just not known to me, that there was some similar, just like this planar expansion, there's an amount of non-planarity that is our higher order terms in 1 over n and so on. I wonder whether there's a similar thing for other Feynman diagrams. Let's see.
Right, but certainly for finding these Vasiliev invariants, these coefficients, you need the knotted ones, because you're measuring the knot. You're measuring the knot by putting these Feynman feelers onto the knot. And the amazing thing, well, it's because, you know, when you make this expansion, you're creating these terms, but the terms are basically quadratic. I'm sorry, never mind. I just jumped to the end result. Gauss invented a formula for the linking number back in the 1800s.
Okay.
And that's, I'll call the Gauss kernel the kind of thing that you integrate in order to get the linking number of two curves. And you can think of that as a Feynman diagram where you put a point on one curve and a point on the other curve and put a wiggly line between them. And that means integrate on all pairs of points a certain kernel due to Gauss across the product of the two curves. So that Feynman diagram gives the linking number. All the rest of these Feynman diagrams that come out of Witten's integral are generalizations of Gauss.
Huh. So in other words, the propagator, the Feynman diagram propagator becomes this Gauss integral thing.
Yeah.
Interesting. That's all right. We had a few other questions here. So Xerxes was asking, do the Gang-Baxter equations generalize to higher dimensions? Is there a tetrahedral version of them? So I guess that's a question of whether, instead of looking at lines there, that there's a generalization to knots that aren't just one-dimensional, knotted objects.
Yeah, there is.
Okay. Let's see. There's a question from Michael here, which I'm not sure I can represent well, and maybe Michael should say it for himself. He's asking, have you looked into non-commutative Grassmann algebras for knots? Not quite sure what that means. So Michael, do you want to explain what that means?
Yeah, I was just curious because you mentioned the connection with linear algebra, if you thought about how Grassmann algebra comes into the knot picture.
There's a lot of non-commutative algebra that's related to knots in the form of Hopf algebra and Lie algebra, as I mentioned. We've recently been thinking about what people call geometric algebra, which is really closer to Clifford algebra than Grassmann algebra.
I think Michael is an enthusiast of exactly that kind of thing. So, Roger Fenn and I and some other people are thinking about hopefully finding new solutions to the Gang-Baxter equation by way of geometric algebra. We'll let you know.
I've been able to
Sam Lamonaco and Brian. Oh God, sorry, I can't remember everybody's name.
Yeah, I got the trefoil knots with geometric algebra. You can plot it by projecting three-dimensional space into a four-dimensional sphere and doing a rotation in 4 dimensions and going back down to 3 dimensions. That's how you can do it in geometric algebra.
Michael, you should maybe mention that you
say it. Yeah.
Oh, actually, I just wanted to just let you know that. So Michael wrote the Julia package Grassmannian.jl, which is a geometric algebra package for Julia, which is quite well known.
Amongst many other awesome packages. Very
well. Okay, so it sounds like Michael should send Lou his.
Yeah, Michael, send me what you're describing. I'd very much like to see it.
So I have a question. Go ahead, Michael. Did you?
I just said all right.
Yeah. Okay. So if I might just change topic a little bit, I'm curious. I know that Lou has also been interested in the laws of form and all of these various minimal Boolean algebra kinds of things. First question is there a connection between your knot theory work and your interest in things like laws of form and so on, or are those two separate interests? I've never been clear about this.
In my mind, there's certainly a connection. For example, the laws of formality, which is based on two moves that you can do on some expressions, reminds me always of Reidemeister moves. It's sort of like Reidemeister moves. You have these two moves.
Maybe we should give some context here. I mean, this is
well,
about Boolean algebra.
Right. Let me try to give you some concise context. Maybe you can answer a question too. I'm going to describe this the way it's described on the Wolfram wiki. I forget what you call the Wolfram wiki.
Math World.
Math World, yes. And if you look it up in Math World, it would say this laws of form is about form, and it's based on a couple of axioms about dealing with forms. The axioms are that if you put two forms next to one another, they can be replaced by a single form. And if you let one form take another form as its argument, it can vanish. I was wondering who authored those words that way.
Interesting question. Let me look at them. That might have been, it might be something that comes out of my NKS book. I don't know. I'm now embarrassed.
It could be you.
Yes, it could be me. That's because I was trying to understand the relationship to let me see. Gosh, where am I even finding this? I mean so I'm not sure, but I have to find it. And I'm not sure I would necessarily recognize it. But I mean just the context here is this is a way of writing down Boolean algebra using I mean, in a diagrammatic way of writing down Boolean algebra.
Well, you could think of it as having started that way, but I prefer to think of it on its own grounds, that it is a way of speaking of form, where we take the form of distinction for the form. So when I represent form, I represent it as some form of distinction. And this is analogous to number. I represent the number 2 by an instantiation of the number 2, like 2 slashes. I represent form by something that has form, like a circle or a right angle bracket, and it has form in as much as it makes a distinction in the space upon which it is inscribed or written. So I'm beginning there. And that means that when I write a form, some form like that one, Spencer Brown's notation, then it is actually referring to itself along with referring to something else, perhaps, because it itself is a form, a distinction. Of course, the same is true of the number 2. If I write down this for the number 2, it refers to any couple, including itself. So there's nothing strange about this except to become conscious of it. It seems a little strange because we're usually unconscious of that movement. Anyway, there are these two rules that if you put two things next to one another, it becomes just one of them and it can cancel itself. And this could be motivated by thinking of what it means to be taken as an argument. It could mean that you cross the boundary of a distinction that is indicated on the inside. If you cross from what's on the inside, then you're on the outside. If you cross from the marked state, you're unmarked. If you cross from the unmarked state, you're marked. So cross over cross is unmarked. And cross next to cross is like saying the name of something twice. Now, the issues of crossing a boundary or going from one side of its distinction to another, or of saying the name of something, of course, are fundamentally the same issues that Boole is considering. So it isn't surprising that this is going to be a model for Boolean logic, and it is. But when you make a model for Boolean logic out of it, the mark is separated into the complementation operator. Boolean logic has a separate complementation operator and two values, 0 and 1. So this system that I just described is differentiated a little bit to become Boolean.
Although it also has a, I mean, but you have an operation which is the adjacency operation of 2 marks, and you also have the nesting operation of 2 marks, as I understand it. And those
Right.
are, so you've traded off kind of, in a sense, the true false thing is being traded off for having these 2 operations. I mean, you might, okay, in Boolean algebra, we know that you can have just NAND as a functionally complete thing, but then you have to have true and false as the values. What you're saying here is you only have to have one thing as like a value, but then you have 2 operations.
Well, I have 2 things I have one thing as a value and I have no thing as the other value.
Fair enough. Fair enough. Okay, but that's I see. Okay. But then isn't, I mean, the single hook thing is that's as a unary form, that's a not. That's like a not. But as a binary form, it's like a NAND. Is that right?
Yeah, it becomes and is A and B in logic is not A or not B. So of course you can make and in the same way here. And it will look like this.
Yep.
So indeed, in binary form, it can produce the and, but in binary form with some negations inside.
But that concatenation of A and the A bar thing and the B bar thing, how am I supposed to read that concatenation? Is that like an
or?
That's like an or. Okay.
Mhm.
And then so it's a not of an or. Okay. So that's
nothing startling at that point. No.
Right. But so now there's a lot you can obviously do, as you can in Boolean algebra, of looking at equivalences between different different forms and so on. I'm curious, is there some geometrical or not theoretic way to think about those equivalences? Is that I mean, when you say, this expression is equivalent to this other expression, are you able to sort of entrain ideas from topology, knots, geometry, or whatever, and thinking about those kinds of things?
Well, it begins to feel like knot theory when you are looking at systems with feedback, at systems with self-reference in them, because then you have a lot of circularities in your graphs.
And when you say self-reference,
yeah.
What is that, when you define self-reference, is it like saying A equals some expression with these operators that contains an A? Is that what you mean by self-reference?
Yes.
So it's like a functional equation.
Well, actually, I call that reentry, and I don't use self-reference so much, but I just used it a moment ago, right?
Right, but so in a sense, you're defining a functional equation of some kind. So if I were to say A equals, so in some sense, I'm not quite understanding. I mean, in Boolean algebra, an equation in Boolean algebra, I'm now a little bit confused. I mean, if I just write down an equation in Boolean algebra with variables in it, then I see. It's if it isn't it could be a tautology, but if it isn't a tautology, there will be a particular assignment of truth values to those variables, which will make that satisfiable.
Or it might be not satisfiable, like this little equation here.
Right. Yeah. Right. At least if you're not right in
I mean, not Boolean satisfiable. Yeah.
Yes. Right. But so what you're saying is that the solution set, in effect, you have some equation which has a bunch of variables in it, and it has some solution set which are the satisfiable instances of that collection of variables, if I'm understanding correctly.
True, but if I write a reentry equation, it could mean it could mean something which has states that are satisfied. This one I wrote has no Boolean satisfied states. It would oscillate if I think of it at all, right? F equals F cross is the Lyra, so it oscillates. If F is marked, it becomes unmarked. If it's unmarked, it becomes marked. And that's interesting to think about. But suppose I did this one, F equals that. Now, that doesn't look like I did anything at all. I just have a double cross.
Yep.
It's satisfied by any F. But if I look at it as a feedback circuit, then it's this, where my element, my NOR gate, is this guy here. So I mean, this is a NOR gate. This is the mark as a gate.
Uh-huh.
And then this is a memory element. It could be that this is marked and that's unmarked, and it will hold itself up that way, marked, producing unmarked, producing marked.
But so this is I mean, in a sense, this is a sort of a breaking apart of the notion of an equal sign to something where you're saying, instead of that being an instantaneous equal sign, it is a transformation from one side to the other that takes sort of a time step to happen. So in other words, you're saying there's an F.
Yes, so you can look at it either way. You can say that it means the interconnected structure that is out of time having that property, which is this graph.
Uh-huh.
Or you can think of it as a time step. But once you have the graph, then you get to think about it another way. It's a system with stable states. If F is marked, then the inner part here being unmarked, they can, out of time, just hold in that pattern. Low voltage, high voltage, and they hold in that pattern.
Yes, okay, fair enough.
And in some flip-flop circuits in computers, that's how memory is happening.
How memory used to happen back in the day, Williams
right.
tubes or whatever. But, but I'm still a little okay. So you're thinking of I mean, in things like solid automata and so on, one's always thinking about, one has these Boolean operations effectively, and in a series of time steps, you're applying those Boolean operations. And I had never really understood that you're, when you write an equal sign and you have a reentrant thing, you're basically thinking about that as a process where you're going around the equal sign, so to speak, where you're I mean, you can think about it that way, and you can ask the question, but I mean, then presumably.
Well, I may want to think about it both ways. I may, right? So, for example, suppose that I were to take a journey off into an infinite form, like a nest of these boxes, like that, right?
Yep.
Well, then, and call it J, then J is topologically identical, but I would just write identical to J with one more mark on it.
Yes.
But actually, if you think about it, you really are meaning that you knew how to shift the whole system up one.
Yes.
It's Hilbert's Hotel. Everybody moves up one room, and there's no end to it.
No, I understand the setup. I'm just trying to understand the relationship to anything that I understand. So okay, so you've got this idea of essentially the self-consistency, but the thing I'm trying to understand, these are equations, and equations, you know, there is a solution set to these equations in some sense. And is that the way you're thinking about it, or is that not? I mean, you're describing it.
It depends on what I'm doing. If I were if I wanted to write a cellular automaton in this notation, then I might write A equals something involving B, C, and D, and so on. And I would probably mean the next A and the next B and the next C when I wrote it that way, right? And I might, for shorthand, just write it without writing A prime or AN plus 1.
I see. I see. Okay, fair enough.
But sometimes I might mean it to describe the graphical structure. And then I wouldn't have to have a time step. It's similar to non-well-founded set theory will define the set omega, which is equal to its own member, by drawing a node in a graph and a cycle edge pointing back into the graph, right?
Yes.
Because pointer means belongs to, and this dot belongs to itself. So it's equal to its own member thing.
So, I mean,
but maybe you want to think about that recursively. There is, I think I have fun, but I might confuse somebody else by writing it one way and thinking about it another.
Yeah, I mean, there's a question of, is it an infinite data structure, in effect, kind of existing at a moment, or is it a process that is, you know, that is being generated through time? I mean, that's and you might think of those as equivalent.
Mm-hmm.
I mean, but from a computational point of view, they don't feel equivalent, because you can't necessarily, it might take infinite computational effort to get that infinitely iterated object. But I'm curious, I mean, okay, so you've got this connection of these reentrant expressions from laws of form and so on. Does that directly lead you to something geometrical or topological, or are you now about to pull out a trefoil knot that you can make from an expression in laws of form?
Well, I think of them as relatives to one another. For example, I think, let me see, I'll write you a bit of algebra. If I label the arcs in the diagram like this, right? A, B, and C at a crossing, yeah? Then I can write C is equal to some kind of product of A and B, right? Maybe I'll write it as AB cross just to make it look like laws of form, but it's just some kind of product of A and B, right?
Yep.
All right. Well then, what I would like is that product would give me an algebra, and then I would write a system of relations, and I wouldn't be wanting to solve them so much as, let's just write the simplest one I could. A, and A cross coming out, so A equals A cross. This would be what happens to that little curl.
What? Wait a minute, what happens here?
I'm sorry, let me start again on a blank sheet of paper.
Maybe other people understood this. That was too.
I wrote too much. Here's a little topological entity.
Yep.
Okay.
Yep.
And let me write A and A here, and of course it goes all the way up around. But let's not connect it to itself yet. And by my rule, what comes out, A meets A, A meets A, and comes out A operated on by A.
Yes.
Okay. And then if I close the topological circuit, then I would have A is equal to A operated on by A, and I would have an equation of that kind.
Okay.
Now I might say, I would like to solve the equation, but I may solve it in an algebra that has some property that has that property, right? I might well. If we if we went all the way to the trefoil knot, it would be more interesting because we would have a set of equations for A, B, and C.
Yep.
And I'll write them. Let me see. I have C is equal to A operated on by B, and B is equal to C operated on by A, and A is equal to apparently B operated on by C. So I have a system of equations like that.
Mm-hmm.
So then operating in modern algebra, I wouldn't say that I already knew what the solution should be. I would say I create an algebra in which these equations are true.
That's
And
cool.
then
Yeah.
and then I also want the algebra to satisfy certain general identities corresponding to Reidemeister's moves.
Okay.
So
Okay.
those are the axioms. We can write them down. You just take Reidemeister's moves and they'll have general identities, 3 general identities, and these specific ones. And then if I can find an instantiation of that algebra, I will have found a topological property of the knot mirrored in the algebra.
That's very interesting. Is this in, I have this feeling that I've noticed this in some book of yours, and I completely didn't understand what else was going on.
Sure. I discussed that in all the different books I wrote, I think.
Okay, fair enough.
But the unknots, it's in unknots.
So I mean, the big picture here is you're giving this correspondence between this algebra and the sort of topological structure of this knot. And I'm just trying to understand, how general is that idea of going from an algebra to some kind of knot-like topological thing?
Well, it is part and parcel of the kind of thing that topologists do in general. They have some transformations on their spaces and they try to image it in algebra. They try to get a functor from the topological category over into an algebra category in some way. It becomes very concrete in the case of the knot theory, in some cases.
Fair enough. Actually, the algebra that works here is an amusingly simple algebra. You have 3 elements, A, B, and C. And you should have that A combined with B should be C. Okay.
Any 2 different ones combined to the third. And any individual one will combine with itself to produce itself.
Okay.
Well, that's a very elemental algebra. It's related to the integers mod 3, of course, but I feel like it's sort of what laws of form would have been if someone had started with topology rather than Boolean algebra.
But so, okay, so if you go to bigger knots, you get presumably other axioms that correspond to bigger knots.
Well, you get the same axioms for that algebra, but you get different algebras.
Fair enough. But so how do they, I mean, you said that one's mod 3, integers mod 3. So what's the corresponding mathematical interpretation of the algebras that you get for other kinds of knots?
Well, at this first level or entry level thing, you can associate the integers mod n to any given knot, and the n is a number you can figure out for that knot. What?
But different knots, 2 different knots can give the same algebra, or how does that work?
They can, yeah.
I see.
Yeah. I might as well be real concrete about this so you see how it would work and somebody listening could fool around with it. I'm going to define the operation to be simple and arithmetical. It's going to be twice b minus a in integers or in some modular number system.
Okay.
Okay. So you take twice the overline minus the incoming line. That's the gate. Well, then you will notice that it works well for the Reidemeister move. Suppose you had A, then it would be 2a minus a, which is a.
Okay.
That's good, right? Because if you did the Reidemeister move, you wouldn't be able to see that anything had happened.
Right.
And you can check that the same thing will happen with the other Reidemeister moves. So then you take your knot. This is quite amusing. Let's take the trefoil knot. I think it's amusing anyway. I just put some numbers on it, like 0 and 1. Okay, 0 and 1 on the trefoil knot. There, and then I propagate. So 2 times 1 minus 0 is 2. And 2 times 2 minus 1 is 3. And I have a paradox, but in modern life, that's no paradox. 0 equals 3. So I'm in Z mod 3. Well, if you took another knot, you might get Z mod 5. If you took another knot, you might get Z mod 1205 or whatever. Every knot has a number, and some have 0, and this doesn't work for them.
So
Do the groups ever get more interesting than cyclic groups? You said it for an elementary
Oh,
level. It
yeah,
almost made it feel like you were hiding something.
Oh,
You
I'm
said that.
hiding lots of non-commutative things like the fundamental group that can be described in a similar way, and other algebra.
So let's see, I think Raphael had another question here about category theory and was asking, can knots also form monoidal categories? Is that important or useful? In other words,
Yes.
is there some kind of monoidal combination of knots, I guess?
Yeah. Well, a braided monoidal category, a braided monoidal tensor category, roughly speaking, what I mean by that is that I should be able to take 2 morphisms in the category and place them next to one another and get a new morphism. And I should have some notion of braiding, like in knotting. So it's kind of clear that if you had knots in there, it ought to be braided, whatever braided means. I mean the following sort of thing. Let's consider a bit of tangle like this. And this is supposed to be the direction of morphism here, right? So this is a morphism from the object 1 to the object 2, counting the number of lines. It's categories. Objects have no structure. All the structure is in the morphism. Here, that's natural. It's just this braiding going on, but it's more than braiding. Here's an interesting little piece of morphism that goes from 0, and there is a 0 object, to 1 to 2, right? So we ended up going from 1 to 3 through 0. And so on. So here's a morphism in a braided tensor category. And you compose by sticking the lines together, and of course you take them up to topological equivalence. And so
Does this allow you? Oh,
go ahead.
I was going to say, does this allow you to think of knots as finite or discrete, just like you have finite topological spaces? Can you use this sort of category theoretic way to sort of think about, like, I don't even know if this word makes sense, like discrete or finite knots, because it almost seems like you're decomposing it into these like morphisms that are sort of atomic.
Well, I am. That's right. So whatever knot or tangle I have in mind, the basic morphisms that generate this category are the ones that I'm writing down here. They are the identity from 1 to 1, cups and caps, crossings. And because it's a tensor category and I can put things next to one another, I get a huge, I can draw any knot or tangle I like, right? And then the morphism, then you take a functor from that category into, say, linear maps of vector spaces, and it can give you powerful invariance. It'll give you Jones polynomial and all those things if you choose your matrices right.
So I'm still trying to understand. I mean,
Excuse me, did Bob Cooker talk about categories like this? Because he uses them for quantum mechanics and he uses them for linguistics.
That's why it's on my mind, actually.
And you're going to see identities that we have reinterpreted in terms of adjoint functors and linguistic syntactic transformations, all sorts of things.
What's a good reference
categories
for
are very fascinating in that some piece of structure can map into all sorts of different things, right?
Yes. Yeah, no.
Is there a good reference that talks about this way of looking at knots in this sort of categorical language that you would recommend? Because this is really cool. I just don't know a lot about knots.
Well, my book Knots in Physics does to some extent, and some of my papers do. And then there's probably lots of other things I could point you to.
Let's see. So there were a few comments here. David, Marcelo, Raphael. No, sorry. David is talking about things I don't understand here. So David, do you want to say
David
something
Chester?
here? Yes.
Yeah.
Do you want
Well,
to
I was just pointing out that well, Schwinger didn't really believe in QCD, but he thought that the strong force was modeled with preons, but it was eventually figured out that you can have this preonic knot model. A bunch of people have discovered this actually independently. And so it kind of unifies Schwinger with QCD. But we also, to turn it into a question, it seems that electromagnetic plane waves with special conformal transformations can be turned into knots of light, which exhibit scattering properties that can lead to bound states. So my question was, if we're looking for some unified field theory, is there anything we should look for in gravity that relates to conformal gravity, since we know that if we're looking for knotted excitations and we know the special conformal group is related here?
Could you excuse me for a moment? My telephone is ringing. I'll be right back.
No one has really looked into like knots of Yang-Mills plane waves, for instance. Well, actually, that's not true. Someone did.
I remember seeing.
Someone did.
There's a recent enthusiasm for knotted electromagnetic fields.
Exactly. People haven't really extended a lot of that analysis to Yang-Mills theory yet, but there is some work on arbitrary spin Hopfions to infinite spin that's been done.
It's can we mute? Let's see, hold on a second. Let me just.
Oh yeah, and in that model they use this thing, like they twist the braids as well. So you have strings and you can braid the strings, or you can twist the string and then braid it. And so the preonic knot model uses this notion of twist.
So are you talking about the Sundance Bilson-Thompson thing?
Yeah, I'm actually more familiar with the work by Robert Finkelstein at UCLA, because he talked to Schwinger.
I think that's source.
It's the same thing.
From. Yeah. Well,
he didn't realize that. Same thing.
I'm sorry. I think I saw his papers, or maybe I'm thinking of somebody else. You say he didn't realize that the Sundance model was around?
Right. He cited Shoup and Harari and followed up on some of their observations, some obscure work from the 80s.
Maybe you could send me a reference to the Finkelstein. I might have missed something there, because I'm familiar with the Sundance Bilson-Thompson thing.
I'm pretty sure it's the same thing, except the mathematics looked more detailed for Finkelstein.
But so
well, that's why I'd like to see. Yeah.
Send it along, right? So I mean, there's been some recent enthusiasm for knotted configurations of the electromagnetic field, as
right, and some of that is a matter of just sort of making it.
Right.
Yeah,
we were asked to consult on some weird movie recently, which and we were trying to sell them on having knotted electromagnetic fields, because we thought it would be it would be good for the movie and also really cool as an effect, as a visual effect, to have a knotted tokamak, for example. Tokamaks usually.
Yeah, I used to joke. Maybe it's not a joke that if they would knot the tokamak, it would work.
Yes, well, quite right. I mean, that hasn't happened yet, because I mean the issue with tokamaks is always, where are the resonances, and you'd presumably avoid a lot of those by having it be knotted.
There is a Wendelstein plasma, I think,
right.
experiment.
Yeah,
that
in
has the
Germany.
knotted.
Oh yeah, that's right. That's right. We had pictures of that. That's right. I remember now that we were showing pictures of that to the special effects people. Yes. Yeah, you're absolutely right. There is a knotted tokamak. So we should.
Wow. And does it work?
Let's see. Can
It
somebody bring
worked
up
for
a
like
picture?
a fraction of a second, I think, but I might not be a tokamak. It might be like a different. It's called a stellarator.
Yeah,
think.
that's right. That's the other kind of. Let's see whether we can bring up a picture here. Is this really knotted? Let me see. Well, Lou will know immediately whether it's knotted because he's. Let's see here. This seems to be the. That's the picture of the object. It doesn't look. It looks. Well, I don't know whether these field lines. I can't tell something like that. But yeah, I think that there's a physical instantiation that is this thing here. So here we'll send you the link to this guy.
Please do. Yeah.
And we'll find out if it's truly knotted or not.
Louis, I put a link in the chat. I don't know if you'll see it. Otherwise, I can try to email to you later.
Yeah, I saw the link to Finkelstein. Oh, you made a link to Hopfion's and Wendelstein. I see. Yes.
No, that's the Wendelstein ones. Is that? Oh, wait a minute. Is this the? I'm confused by this classification of electromagnetic and gravitational Hopfions.
So yeah, the electromagnetic Hopfions have been measured in an experiment, and this generalizes the math to arbitrary spin for linearized waves.
What is? Tell us what a Hopfion is.
It's a Hopf soliton. It's a solitonic Hopf quasi-particle.
It's like a vortex.
And you mean that it has the topological form of a Hopf link?
I believe that's the idea.
I believe it's just like a vortex knot. Like if you take a knot, but you make it a vector field, and then you throw it in some space, it rotates around.
Okay. Well, let's see. It's getting late here, so and it's we should probably wrap up soon. But do we have there are lots of great questions and topics, I think, but maybe we've touched on at least some of. Have we hit some of Lou? Have we hit some of your greatest hits, or did we miss most of the greatest hits here?
No, you hit on lots of my favorite things. Yes.
Okay, that's always good.
I'll mention one thing that we haven't talked about that I would enjoy discussing at some point, and that is there is a project that I've been working on for a long time, which I call non-commutative worlds, which involves thinking about how it's really what comes out of thinking about how discrete calculus doesn't satisfy the Leibniz rule, but if you correct it, it turns out that what you're doing are commutators, because a derivative, taking the commutator with something is the same as a derivation, and you can reformulate discrete calculus in terms of commutators. And then a lot of things that happen in physics are related to that, which means that a lot of things that happen quite normally in physics are related to the discrete through that channel.
Is this like Baker Campbell Hausdorff formula type use of combinations? I mean, of commutators? Is that how it comes out?
No, but I mean the following very simple thing, that if you define f of x is equal to the commutator of x with h, where h is somebody, well, then you can check that the Leibniz rule is true.
Okay.
Right? In other words, that FG, the derivative, what am I saying? The derivative of X is the commutator of X with H. Okay? So
Okay.
then the derivative of X times Y in a non-commutative associative framework will be equal to the derivative of X times Y plus X times the derivative of Y. Taking commutators is a derivation.
Okay.
Abstract algebra point, but if you correct discrete derivatives in the right way, they turn into commutators.
Okay.
I can make that clearer if you like, but I don't know.
I would
whether-
also say on this point, because I'm very interested in this, there's multiple dimensions when you do discrete calculus. Leibniz rule is one, but the product rule, associativity of cochains, commutativity, there's like all these things
Oh
that
yeah,
break.
sure. That's
They all-
certainly true. That's true.
So each way of doing the discrete
and-
calculus, you're
Mhm.
picking, and it's not clear what those trade-offs are.
Yeah, that's right. That's why I would tell you my story about developing something starting from the point that I'm making. But it's a shaggy dog story. It should be for another time. Yeah.
Probably for another time. Actually, I'm curious in the I mean, some of these discrete physics, there's this sort of tradition, which I don't know much about, the whole ANPA, natural philosophy, discrete physics story.
Yes. Mhm.
Is that, how does that weave in with any of these other things, or is that a completely separate branch?
Well, for me, it weaves in because I spent most of the time that I talked about this kind of discrete thing that I'm telling you about just now. I spent most of my time telling that to AMPA people because I happened to go to their conference many times. But that isn't an original AMPA theme. The original AMPA theme came from trying to think about discrimination and discrimination of discrimination in a very almost philosophical way by a linguist named Frederick Parker Rhodes, and then by physicists Clive Kilmister and Pierre Noyes and others, and Ted Bastin, and they were trying to build this hierarchy of discriminations and match it with physics.
I've never understood this stuff, right?
I have never understood that stuff either. I mean, you can find some of it published, but it's very hard to see how it really turns into physics. They kept hoping.
I see. But now Parker Rhodes was, I mean, he had a very colorful story, which I now forget. In, I mean, is there a, you presumably knew him?
No, I didn't know him. He had passed away by the time I met the AMPA group.
Oh, okay. But so at the time, so was it Pierre Noyes? Was he the main sort of the anchor person, so to speak, of the ANPA?
Pretty much at that time in the mid 80s.
Right. And what was, I mean, so you also never really understood, because I've never really understood what they, I mean, I've seen.
Well, of course, Pierre had the idea that he would do everything with bit strings.
Yes.
He was trying. And I don't know, he might have even dabbled in cellular automata. After all, bit strings can be that. But I don't think anything ever really focused and did fundamental physics out of that. It just comes close sometimes.
Right.
Others in that group may feel differently.
Right. Well, right. No, I've been trying to track down as a chap called John Amson, who's now in his mid-90s.
Oh yeah.
Who I rather enjoy, and he's been sending me a little bit of information about sort of the history of this discrete physics stuff. Although his own interests, I think, have gone much more in the cellular automaton direction, and that part I understand. Turns out also he turns out to be a world expert on tides, which I had no idea about. And so he's been just recently helping us actually with trying to understand, people say Newton solved the problem of tides, but it isn't true. The actual problem of tides on, realistic ocean tides is a really complicated story. And he happens to be a person. So it's a weird connection which I had only just recently made. Well, we should probably. I'd like to hear the story of commutator physics, so to speak, and I'm sure other people would too. But we should probably wrap up here for now, and thanks very much for very interesting conversation, and I think no doubt, if nothing else, there'll be a bunch of people here who'll go out and buy your books. I've already got your books, so that's always a start. Okay, anybody, any further comments from anybody, and then.
I also
Well.
would like to hear the discrete geometry story, the shaggy dog story. But
Right, we'll have to set up a
Yeah,
time
me
for
too, sometime.
Okay, well, I'm willing.
Okay, sounds good. All right, we'll shaggy dog, a date with a shaggy dog at some point.
That's
All right,
it.
well, so thanks very much, and
Thanks so much.
good night. Yeah.
Well, thank you.
Okay.
night,
Thank you very much.
Bye.
Thank you very
Thanks,
much.
everyone.
Cheers.